This video will introduce the series on the basic knowledge of the spectroelectrochemical method, Chapter 4, Optically Transparent Thin Layer Spectroelectrochemistry, Part 1. The content summary of this chapter is here. We will introduce the measurement of optically transparent thin layer cell to obtain the quantitative standard electrode potential and the electron transfer number. This chapter will be divided in 3 parts, as follows. 1. Reversible reaction. 2. Quasi-reversible reaction. 3. Biological redox system using mediators. For a reversible reaction system, the electrode potential can be expressed by the Nernst equation. When potential is applied to the system, in order to satisfy the above equation, the substance undergoes an oxidation and reduction reactions on the electrode surface, which is generated by the current. Although the potential applied controls the concentration ratio of the substance on the electrode surface, the concentration ratio in the solution is quickly adjusted to the same ratio as at the electrode surface due to the thin layer of solution in the thin cell. The time to equilibrium depends on the thickness of the thin layer of solution. Generally for thin layer cells with a thickness of less than 0.2 mm, electrolysis reaches equilibrium when the current decays to a minimum value, usually within 60 seconds. Therefore, the potential E can be plotted against log of concentration of the oxidized form per concentration of the reduced form to obtain a straight line. According to the slope of the line can be found the number of electron transfers N. The standard electrode potential can be obtained from the intercept of the line on the potential axis, and as the current through the electrode is very small when equilibrium is reached, the effect of the IR drop can be ignored and the standard electrode potential can generally be determined to a few millivolts. For a reversible reaction system, the electrode potential can be expressed by the Nernst equation. When potential is applied to the system, in order to satisfy the above equation, the substance undergoes an oxidation and reduction reactions on the electrode surface, which is generated by the current. Although the potential applied controls the concentration ratio of the substance on the electrode surface, the concentration ratio in the solution is quickly adjusted to the same ratio as at the electrode surface due to the thin layer of solution in the thin cell. The reversible system, potassium ferrocyanide, is illustrated below as an example. Figure 4.1 shows the absorption spectrum recorded at different applied potentials. The absorption spectra were recorded at different applied potentials, starting at 0.4 and waiting for complete equilibrium after each change in potential. The absorption value at 420 nanometer was chosen as a measure of potassium ferrocyanide and potassium ferrocyanide. For a reversible reaction system, the electrode potential can be expressed by the Nernst equation. When potential is applied to the system, in order to satisfy the above equation, the substance undergoes an oxidation and reduction reactions on the electrode surface, which is generated by the current. Although the potential applied controls the concentration ratio of the substance on the electrode surface, the concentration ratio in the solution is quickly adjusted to the same ratio as at the electrode surface due to the thin layer of solution in the thin cell. Set at 420 New Mexico. Molar extinction coefficient of ferrocyanide. Molar extinction coefficient of ferrocyanide. Thin layer cell path length. Ferrocyanide ion initial concentration. Here, absorbance when completely oxidized, equation 4.4. Absorbance when completely reduced, equation 4.5. Absorbance at an arbitrary intermediate potential, equation 4.6. And the concentration when there is no chemical reaction, equation 4.7. The concentration for oxidation reaction, equation 4.8. And, the concentration for the reduction reaction, equation 4.9. Substituting the above 2 equations into Nernst equation, we get. In the formula, A red is the absorbance when the ferrocyanide ion is completely reduced to the ferrocyanide ion. Then, plotting the applied voltage against concentration ratio gives a straight line. Figure 4.2 shows a straight line obtained from the Nernst plot for the potassium ferrocyanide system with a slope of 59.6 mV and a calculated electron transfer number of 0.99, corresponding to a single electron electrode reaction. The intercept gives the equation for the potential cell potential equal 0.275 volts versus saturated calomel electrode. The standard deviation of the four measurements was 0.001, which is in general agreement with the values reported in the literature. It is important in this experiment that the solution is in equilibrium with the electrode potential and that all changes in light absorption cease when the measurement is carried out. Only a small residual current and a small current due to edge effects pass through the working electrode. Thin layer spectroelectrochemistry provides the most effective means of studying redox pairs that exhibit slow heterogeneous electron transfer at the electrode. Thin layer spectroscopic potential experiments can be a very slow electrochemical technique, due to the fact that each applied voltage is maintained until the light signal change is completely stopped. Therefore, for slow electrode kinetics, the potential can be held long enough time to achieve that a change in the optical response signal can be observed even if the Faraday current response is completely masked by the residual current. A typical example of this type of system is the vitamin B12 mentioned in Chapter 1, where the rate of electron transfer in the first electron reduction step is rather slow, even though the reduction wave is barely observed below the slow sweep used in the DC polar spectrum until the potential is sufficiently negative to produce a 2-electron reduction wave. Figure 4.3 shows the cyclic voltammogram for its negative potential sweep. At EPC equal to -0.93 volts versus the SCE potential, a 2-electron reduction peak is shown. In contrast, the thin layer spectroscopy constant potential experiment shows two consecutive, easily distinguishable 1-electron reduction steps. Using a mercury gold mesh grid optical transparent thin layer spectroelectrochemical cell with a progressive potential applied from -0.10 volts to -1.15 volts, two clear changes were observed in the UV-vis spectrum of the B12 solution, one change occurring in the potential range of -0.58 to -0.75 volts, as shown in figure 44. The starting spectrum at -0.55 volts is derived from the initial B12, characteristic of trivalent cobalt, with an absorption band at wavelengths from 350 to 360 nanometer. A gradual step towards negative potentials most produces the absorption spectrum of B12 at -0.77 volts, for example divalent cobalt, and Nernst plotting using absorbance data at 360 and 311 nanometer indicates that the spectral change corresponds to a 1-electron reduction process with half-wave potential equal -0.655 volt. The second spectral change occurs in the potential range of -0.77 to -0.95 volts. For example, as shown in figures 4-5, the starting spectrum at -0.770 volts is that of B12, example divalent cobalt, which gradually steps towards the negative potential to produce a spectrum of B12, monovalent cobalt, at -1.000 volts. The absorbance data at 368 nanometer were plotted by Nernst to show that this change in absorbance also corresponds to a 1-electron reduction process with the formula potential half-wave potential equal -0.880 volts. Many biological substances such as hemoglobin and myoglobin have a very slow direct heterogeneous electron transfer rate at the electrode. This behavior is usually due to their strong adsorption on the electrode surface and the fact that the electroactive center is surrounded by their polypeptide chains, and these biological substances are difficult to study using the usual electrochemical methods. For such systems, the usual method is to add a mediator to the solution to regulate the electron transfer between the electrode and the biological component, based on the principle that, where M and B represent the mediator and the biomolecule respectively, the biomolecule cell potential and number of electrons values are obtained from the added potential and the LNOB/RB obtained from light absorption in a Nernst diagram similar to equation. Taking cytochrome C as an example, cytochrome C has no obvious redox peak in the gold mesh grid electrode optically transparent thin layer cell, but when 2,6-dichlorophenol indophenol is added to the solution as a mediator, the rate of oxidation reduction of cytochrome C is greatly increased by reacting with dichlorowandophenol. The spectra of cytochrome C at different potentials are shown in figures 4-6. Cytochrome C was completely oxidized at 300 mV versus saturated calomel electrode and completely reduced at -600 mV versus saturated calomel electrode, and the spectra were recorded under equilibrium conditions. For example, the current dropped to negligible levels and the changes in the spectra ceased. The applied potential takes approximately 10 minutes to reach equilibrium for each change in applied potential, and this equilibrium time is related to the concentration of the medium and the design of the optically transparent thin layer cell. The intercept and slope obtained from the Nernst plot of cytochrome C give B0 equals 0.261 plus minus 0.001 volts versus normal hydrogen electrode and A equal 1 at 25 degrees Celsius, respectively. Therefore, for the electrochemically irreversible biological redox system on the gold electrode, a very accurate formula of biomolecular cell potential can be obtained. For some biological systems, it is very important to measure cell potential to control the solution potential through the redox of the mediator and biological components. For example, in the absence of a medium, it takes several hours to electrolyze cytochrome C in an optically transparent thin layer cell, but only a few minutes with a suitable medium. The basic requirements for selecting a mediator are: the mediator must quickly and reversibly exchange heterogeneous electrons with the electrode and transfer homogeneous electrons with biomolecules. Stable in both the oxidized and reduced states. Its spectrum does not overlap with the spectrum of biological components. The thin layer spectroelectrochemical method can also be used to easily determine the thermodynamic function of the system. The thin layer spectroelectrochemical method can also be used to easily determine the thermodynamic function of the system. At different temperatures, the potential log of oxidized and reduced concentration relationship curve of the same system is measured, and the thermodynamic parameters such as delta entropy and delta enthalpy can be obtained from the measured equation cell potential with the temperature change. This concludes the fourth part of the series on the basic knowledge of the spectroelectrochemical method, optically transparent thin layer spectroelectrochemistry, Part 1.